Meet the plant that turns natural gas into liquid at -162 degrees Celsius, while floating on the open ocean, nearly half a kilometer long, weighing 660,000 tons, held by 16 mooring lines through cyclones. Offloaded to carriers with no port in sight. We break down how the whole thing gets built, moored, and kept alive offshore. The last section reveals a maintenance strategy unlike what you'd expect. This is not a video about energy in general. This is what happens when someone decides to build a gas plant on a ship. The thing gliding out under tugboat escort is 488 meters long and 74 meters wide, headed 475 kilometers offshore. Bigger than any aircraft carrier ever floated, and it makes gas for a living. Now picture towing that same monster 5,800 kilometers across open ocean. The hull left the shipyard in South Korea and crawled to Australia at the pace of a jogger, escorted the whole way. Once it arrives, the process begins. Cool natural gas to -162 degrees Celsius. Watch it shrink 600 times and pump it into carriers. All of it, floating. Some parts are so big they get their own boat ride to the shipyard. The flare boom for Coral Sulf LNG, 424.5 meters long, 66 meters wide, 8 LNG tanks totaling 227,840 cubic meters, was built in one country and shipped to another before being lifted onto the hull. 2 massive cranes, 1 long breath, and nobody blinks. Then comes the turret, the piece that lets the whole floating factory spin with the wind. The lower turret module, the upper turret module, and the swivel access structure get installed piece by heavy lift crane. Get it wrong and the plant fights the ocean forever. Get it right and it just rotates. 250 meters below all this sits an underwater city with no residents. Christmas trees, manifolds, flow lines, anchor piles, all delivered by 10 vessels across 3 countries. Ever tried parking a bus underwater in the dark? These crews do it 4 times. Fully loaded, this thing weighs 660,000 tons, 6 times the largest aircraft carrier afloat. 16 mooring lines, nearly 25,000 chain links, drilled deep into the seabed to hold it through cyclones. But before any of this floats or moors, everything starts with something much less glamorous: raw steel plate. Before the towers, the modules, and anyone paints anything, there is one steel plate laid on blocks. That is where a floating gas plant actually begins. Plasma cutters slice profiles from raw plate. Welders fill the joints. Every centimeter gets logged. A millimeter off here, and the top deck pays the bill. Now scale it up. A hull for a floating gas plant cannot be built one weld at a time by one welder. Gantry robots roll across steel panels the size of tennis courts, laying horizontal, vertical, and transversal welds with software-generated paths that avoid every collision before it happens. We're talking a machine that doesn't take breaks or misread the drawing. Behind that comes ultrasonic testing, X-ray, magnetic particle inspection. Every weld that holds cryogenic liquid at -162 gets checked more thoroughly than most airport passengers. Once the hull is welded together, someone still has to protect all 260,000 tons of steel from the ocean for a quarter of a century. Most ocean-going vessels return to dry dock every 5 years. This one is designed to stay put for 25. Try leaving your car outside for 25 years and see how the paint holds up. Different coats react to different temperatures. Inspectors go through every panel looking for missed final coats, thick spots, anything that could crack years later. One imperfect patch on the outside means an early failure of the steel underneath, and that failure would find you offshore, not in port. Then there's the part nobody films. The arms that transfer liquid gas between two moving vessels at sea. 50,000 engineering hours went into one loading arm. It has to swivel, rotate, and follow a carrier for 15 hours of offloading. Lose the sync, and minus 162-degree liquid ends up somewhere it shouldn't. Inside the hull sit the cargo tanks, 39,000 cubic meters each, tall enough that the crew calls them cathedrals. The flare tower alone reaches 180 meters. The mooring chain? 17 kilometers of it, weighing nearly 10,000 tons, all built to sit in one spot for 25 years. Under the waterline, a different enemy shows up. Barnacles, algae, and salt eating steel faster than any welder can patch it. Self-polishing coatings shed a thin layer of themselves over time, taking marine growth with it. The hull essentially sheds its own skin so nothing can grip. Once the hull is welded, coated, and every tank sealed, the ceremony is short and the tension is long. Blocks come out from underneath. Tugs take position. A hull weighing tens of thousands of tons slides into the water for the first time. Every calculation from every engineer over 3 years gets tested in about 90 seconds. Nobody breathes. Once afloat, the hull becomes a construction site of a different kind. Now the modules can start coming aboard. The real trick isn't lifting them. It's landing them so hundreds of connection points below still line up. The hardest part was never building the hull. It was getting it into the water at exactly the right moment. After 14 months of construction, the floating LNG facility was launched during a narrow tidal window. Nearly half a kilometer long and weighing over 200,000 tons, it then headed for outfitting before gas processing modules were installed. Building the hull is only half the job. The other half looks like a small city of steel sitting on the quayside, waiting. 14 topside modules, 3,000 piping connections, 450 kilometers of cabling, 60,000 pairs of flanges, and every one has to be made right. We've all wrestled a flat pack shelf that came with the wrong bolts. Now imagine 60,000 flanges and no wrong ones allowed. One cargo tank alone holds 39,000 cubic meters of liquefied gas. That's the heart of the process, and it cannot leak, warp, or move. Every module starts inside a hall the size of a small stadium and grows for 3 years before daylight sees it. Grinders throw sparks. Fitters check clearances that matter to the millimeter. Cranes reposition sections that weigh more than most bridges. The module then rolls out on trailers with enough axle lines to make your local highway inspector cry, gets loaded onto a barge, and floats to open sea. This is where every Feelung topside module comes from. A covered hull, an army of welders, and a lifting plan thicker than a phone book. Once it's out, there's no fixing it in comfort. The next time a wrench touches it, there's salt in the air, wind on the deck, and 100 kilometers between the fitter and the nearest hardware store. Look closer at any topside module and it becomes clear. Most of what you're seeing isn't the equipment. It's the piping between the equipment. Each module needs thousands of pipe spools, each cut, welded, tested, and coated before it goes anywhere near the boat. Diameters run from 2 inches up to 60, depending on what's flowing through them. Gas, refrigerant, condensate, seawater, or the flare system. Root passes use one welding process, fill and cap passes another, all programmed against dozens of preset procedures so a robot arm knows exactly how to weld each joint. The choke point on any felling project isn't cranes or steel, it's spools. Get one wrong at the fabrication line, and an entire module waits on the quay while somebody tries to fit a replacement in the 6 inches of space between 2 pumps, so the yards throw everything at getting spools right the first time. X-ray, pressure test, insulation, tagging, tracking. Every spool that leaves clean is one less problem offshore, where problems cost helicopter time. Getting a module out of the hull is one problem. Getting it onto a barge without cracking anything is a bigger one. Self-propelled modular transporters, hundreds of axle lines under one module, creep along at walking pace, steered by a man with a remote control the size of a lunch tray. You've probably reversed a trailer into your driveway. Now try it with a load the length of a football pitch and no room on either side. Sensors track the weight distribution across every axle. Get the balance wrong and one corner sinks. Push it further and the barge starts to list before anyone has time to react. Before any module gets near the water, it has to leave the hull. Twin rows of hydraulic transporters roll a topside out through doors that open like an aircraft hangar. Watch it move at 2 centimeters a second and you'd think nothing's happening. Then you look up and the hull is empty. Then comes the crane show. A power generation module weighing thousands of tons gets lifted off the quay and swung out over open water. Below waits the hull. Rigging teams call this the interesting minute. The crane lifts the module only once, but it has to place it exactly where it belongs. The hardest part comes after the hull is finished. Massive black LPG storage tanks are hauled in on SPM teats, picked up by giant gantry cranes, and lowered into openings built into the hull. The lift is the part everyone watches. Getting the tank to settle exactly where it belongs is what keeps the engineers awake at night. And this is modular construction onshore. Modules built in China, shipped across the Pacific, moved into place on SPMT, and lowered onto their foundations by crane. The last module of one train arrives, everyone cheers, and then somebody remembers there's another train still to come. Once every module is aboard, the system finally works as one. The turret rotates, the hull weather vanes with the wind. The subsea network feeds gas up from 250 meters below. LNG carriers pull alongside for offloading. All of that, floating, in a spot no pipeline ever wanted to reach. Turning gas into liquid at minus 162 is not freezing. It's stripping out water in CO2 first, then dropping the temperature stage by stage inside a heat exchanger the size of a small skyscraper. 50 meters tall, the heart of the whole plant. And this is what that heart looks like from the inside. One spiral wound heat exchanger replaces 5 or 6 conventional shell and tube units. Pure countercurrent flow. Compact, high pressure, high efficiency. On land, you'd give it a whole warehouse. On an FLNG, you give it a corner. Once the gas is cold enough to be a liquid, it has to go somewhere. That somewhere is a tank that could hold a small ocean and lose almost no heat to the outside. Stainless steel plates get rolled into cylinders, welded along seams that get X-rayed and hydrostatically pressure tested. The inner vessel gets wrapped in insulation and dropped inside an outer shell. Then the space between them gets vacuumed out, because vacuum is the best insulator nature ever invented, and it costs nothing to make. Cold shock tests confirm the whole assembly can survive minus 162 without cracking. The bigger the tank, the trickier the roof. LNG tank roofs get built at the bottom of the tank and lifted into place with pressurized air alone. No cranes, no lifting rigs, just fans, patience, and a lot of steel going up. Any cold liquid in a tank slowly warms up and starts to boil off. On an LNG plant, letting that vapor escape means losing product and gaining a fire risk. So a boil-off gas compressor sucks it back, recompresses it, and sends it back into the process. Nothing wasted and vented. Keeping LNG cold also means dealing with the gas that naturally evaporates from storage tanks. Instead of wasting it, boil off gas compressors, capture, and return it to the process. These two-stage reciprocating compressors operate with inlet temperatures down to -160 degrees Celsius, using specially selected steel valves, piston rings, and rider rings built for cryogenic service. Every unit is skid-mounted to simplify transport and installation while fitting into the tight spaces common on LNG facilities. Low vibration, minimal maintenance, because on an FLNG, the maintenance guy might be a helicopter ride away. This is what a full LNG train looks like on land. Modules the size of buildings, storage tanks visible from the coastline, a jetty long enough to load carriers around the clock. Now imagine taking all of that, shrinking it by 3/4, and floating it in cyclone country. At the other extreme, someone tried to do the same job from a trailer. Modular cryogenic units hauled to remote gas wells and cold started in 10 minutes. The trailer proves the principle. The failung proves what happens when the principle gets scaled up 1,000 times while floating. But cryogenic gear on the deck is only half the plant. The other half sits 250 meters below, in the dark. A floating gas plant works only if gas actually reaches it, and gas doesn't rise on its own. It has to be routed up through a network of wellheads, manifolds, flow lines, umbilicals, and risers, all sitting in the dark on the ocean floor. No human ever touches most of it. The plant on the water depends on a plant no one visits. Before the felling has anything to liquefy, someone has to drill the well. Ultra-deepwater drill ships now run blowout preventers at 20,000 CI on the seabed, the first ever deployed at that pressure. Older rigs topped out at 15,000, which meant entire reservoirs sat below reach. That extra layer of pressure capability unlocks fields that used to be untouchable. These ships can also run casing strings almost 4 miles long in one go. 2 ships in the world can do this work, and they cost close to $1 billion each, which is why nobody builds a third one on a whim. Once the wells are drilled, everything needs to be wired together. Umbilicals, bundles of hydraulic lines, electrical cables, and fibre optics get spooled from vessels and laid across the seabed, the nervous system of the whole field. And then there are the flow lines themselves. Pipeline sections get welded together in a yard, floated out on the surface using buoyancy tanks, towed dozens of kilometers by tug, then flooded and sunk into position. The pipe travels on the surface like a raft, then decides to become a pipeline. No expensive pipe lay vessel, no deployment reel, just tow, flood, and settle. But most pipelines don't get towed. They get built on the deck of a specialized vessel, weld by weld, as the ship crawls forward. Individual pipe joints get beveled, preheated, lined up, and welded together. First inside, then outside, by automated systems. Ultrasonic testing checks the seam. The pipe rolls to the next station where the field joint gets coated for corrosion protection, heated smooth, then cooled with water. Over 20,000 kilometers of subsea pipeline have been installed this way. Enough steel pipe to circle the equator half a lap. The vessel moves. The pipe descends. Simple. Any pipe carrying LNG at -162 has to be a pipe inside a pipe, an outer pipe, an inner pipe, vacuum in between, and reflective insulation wrapping the whole thing. Because heat is what turns LNG back into gas, and gas belongs in the compressor, not the pipeline. Vacuum costs nothing to make and insulates better than anything you can buy. Landing a subsea tree at over 7,000 feet is not a metaphor. It's a real thing that happens. The tree weighs roughly as much as a space shuttle. It gets lowered for a full day, then landed on a target less than half an inch across, guided by ROVs with laser precision. All of that before a single molecule of gas moves. And the plant floating on the surface still needs to sit exactly where it started for the next 25 years. At each wellhead sits a subsea Christmas tree, a stack of valves that controls what flows out of the ground. Connecting one to a jumper pipe used to be a nightmare of hard landings, damaged seals, and expensive reruns. The wet tree connector solved that by letting an ROV do the whole thing. The jumper gets lowered from a surface vessel, and ROV lands each end onto the tree using a soft land system, then triggers the hydraulic connector via a hot stab. The connector draws the hubs together, locks the collets, and compresses a metal seal between two mating surfaces. A machine, in the dark, sealing pipe underwater to a standard your bathroom taps could only dream of. Getting a riser from the seabed up through the hull is another job nobody rehearsed on land. A J-tube seal assembly gets installed on the pipe, lowered from a vessel, then guided into a bell mouth by an ROV as the riser is pulled through. A machine threading a needle from a mile away. A floating plant never really stops moving. It heaves, rolls, pitches, and yaws with every wave. The trick is limiting that motion to what the risers, loading arms, and cryogenic pipework can handle. Which starts with mooring chains, a flexible riser, and a ballasted yoke, installed piece by piece before the LNG ever arrives. The anchor for all this is not what you'd picture from a boat. Suction piles are giant, hollow steel cylinders, rolled from plate, welded, coated, and shipped out standing taller than most houses. Once on site, the pile gets lowered to the seabed. Water is then pumped out of the top, and the pressure difference sucks the entire pile down into the mud on its own weight. No pile driver and hammering, just physics, working slowly. Try that with the anchor on your boat. Each pile can hold hundreds of tons of mooring load for decades, and you never see it again. The installation vessel does the delicate part. A dedicated offshore construction vessel with dynamic positioning holds itself over the target while a heave-compensated crane lowers the pile at walking pace. All to place one steel cylinder within centimeters of a mark on a chart in water thousands of meters deep. With the anchors in the seabed, the next problem is connecting the floating plant to them in a way that lets it turn with the wind but not drift. The answer is a tower yoke mooring system, a fixed steel tower planted on 4 jacket legs with a rotating yoke arm reaching out to grip the vessel. The jacket sits on the seabed, gets pile driven deep into the mud, and the top set lands on it and gets welded in place. A yoke arm then connects vessel to tower, letting the whole facility rotate a full 360 degrees with the weather. Wind above the safety limit? Waves too high? The connection waits. Nobody forces a link between a tower and a moving vessel unless the ocean agrees. Once linked, flow hoses, a utility line, and a firewater line follow. The plant is now permanently attached to a spot in the ocean it never chose. But some places don't just have bad weather, they have cyclones. For those, engineers built a mooring system that lets the vessel sail away entirely. Production stops, hoses drain, umbilicals disconnect, personnel evacuate, and the yoke arm gets released and stowed. The plant sails to safe harbor. The moorings sink to a balanced position and ride out the storm underwater. After it passes, the vessel returns and reconnects. Once the plant is producing, the product still has to leave. And that turns the open ocean into the world's most inconvenient port. Any vessel getting close to an FLNG runs on dynamic positioning. GPS, thrusters, and software all fighting the current to hold position within a meter or two. Anchoring doesn't work. Ropes don't work. 2 floating vessels come alongside each other, held by tugs and mooring hawsers. Flexible cryogenic hoses lift from one manifold to the other. At -160, the connection point ices over within minutes. Every steel component contracts, and every joint has to allow for it. Cracks at that temperature don't heal. Ship-to-ship transfer at sea used to be considered impossible for LNG. The loading arms that made it possible took 50,000 engineering hours to design. Each arm has to swivel, rotate, and follow the motion of an offloading carrier for 15 hours straight while both vessels bob independently. First test on a dynamic bench, textbook connection. Then the loading arm retracted too far and collided with itself. The engineers checked, found nothing damaged, and moved on to the harder test. Filling the arm with liquid nitrogen at cryogenic temperatures and triggering an emergency disconnect. Once movement exceeded safe limits, valves closed, the arm broke away, and only a small volume of liquid escaped. Result: very happy team. And this is what a good loading arm actually contains. A swivel joint built from super duplex stainless steel and reinforced Teflon seals, machined to tolerances your local workshop would fail at. A symmetric arm design means virtually no bending load on the jetty structure. Vapor lines can be built directly into the frame. An emergency release coupler guarantees the arm parts safely if anything goes wrong. Quick connect-disconnect couplers make life easier for the operator. Also, a ship and a plant can pass minus 162-degree liquid between them without either party regretting the choice. The certification test is designed to push everything to the limit. Cryogenic conditions, valves triggered, arm releases in a burst of vapor and frost. Everything that should close, closes. Everything that shouldn't leak, doesn't. Certified. And now the arms are docking themselves. Automated systems align the arm to the target on the ship using position data and a 3D simulation. First automatic docking hit a 100% success rate on the trials. The operator basically watched it happen. All of this starts in a factory nobody's ever heard of. CAD models get machined into flanges, ball races, and joints accurate to microns. Coordinate measuring machines check every dimension. Welders finish it. Then it gets barged out and lifted onto a jetty. Precision manufacturing, quietly making sure a ship can offload. And this is where a carrier eventually delivers. A land-based LNG terminal receives the ship, offloads through fixed arms, regasifies the liquid, and sends it into the pipeline network. The floating plant did the hard part. And the ships that carry the product now burn some of it as fuel. Dual-fuel engines run on LNG, low-sulfur oil, or biofuel, and boil-off gas gets captured for combustion. LNG bunkering demand at the world's largest port quadrupled in a single year. The industry made up its mind. Once producing, the plant has to survive the next 25 years without anyone easily reaching it. A floating gas plant is one of the hardest things on Earth to repair. It's offshore, cryogenic, crowded, and cannot stop producing without losing serious money. So most of the maintenance goes to a robot. Roves inspect subsea structures, manipulator arms, open valves, HD cameras check for leaks. Diver time is measured in dollars per second. Rove time is measured in coffee breaks. When a pipeline actually needs work, a specialized frame gets lowered to the seabed. Precision control for lateral and vertical positioning, footprint adjustable for soft ground. The tool that lets a pipeline get cut, coated, or inspected without disturbing anything around it. Behind every one of these projects are years of engineering, thousands of workers, and billions of dollars, all resting on one hull holding steady and one plant staying cold. Coral Sul FLNG stretches over 400 meters, weighs hundreds of thousands of tons, and was built in 3 years across 4 continents, from a discovery on a chart to a carrier full of gas. And that is what it takes to build a floating gas plant. A giant steel hull carries a complete processing facility. At its heart, LNG is cooled to minus 162 degrees Celsius, shrinking its volume about 600 times. Pipelines and subsea equipment feed gas from deep below, while massive mooring systems hold the facility in place. Offshore loading systems transfer LNG to carriers, and a maintenance strategy built almost entirely around robots, because the nearest hardware store is a helicopter ride away. Would you work on one? A place where the commute is a helicopter, the neighbors are all engineers, and the plant under your feet is doing chemistry at temperatures that would freeze mercury solid. Drop it in the comments. 25 years offshore or 25 years anywhere else? And if you learned something today that surprised you, share and subscribe for more videos on the industrial machines that keep the modern world running quietly. See you in the next one. Take care.